The most basic representation of a set in algebra that we're going to see is called a relation. A relation is just a set of ordered pairs. So at the bottom of this slide, you can see a set of ordered pairs that represents the last name and the salary in millions of dollars of the highest paid TV actors and actresses in 2018. All of the visualizations on this screen represent that set. You have a bar graph that represents that set. You can have a chart that represents that set. You can also have other visual representations, like this right here, where we have two circles, where a circle represents the last names of the actor, and then the other circle represents the salaries in millions of dollars for those actors. But all of these represent the same thing. It's called a relation. Again, a relation is just a set of ordered pairs. When we are talking about that set of ordered pairs, we can talk about the first component in that ordered pair. In this case, it was the last name of the actor, is called the domain. And the second component in that ordered pair is called the range of that relation. So I have arrows pointing to each. So the domain, again, is the last name, and then the range would be the earnings in millions of dollars. So if I gave you an example where I asked you to find the domain and the range of this given relation. So let's start with the domain. Again, remember, the domain is the first component of each set. So the domain, in this case, will be the set of numbers that are all in the first component. So 0, 1, 2, and 3 are the first component in each of those. Again, you should always write these in order from lowest to highest when you're listing your numerical components. And then let's go over the range. The range will be the second component, and we have 187, 225, notice the next one is also 225. If you have a repeating component, you do not write it. And the last is 238. All right, so there we go. That is our domain and range for that relation. All right, a function is a special type of relation. And in a function, there is a correspondence from the domain to the range. And this correspondence is very particular. It means that each element in the domain can respond to exactly one element in the range. So you cannot have, like in this picture, we have 1 going to m. So we could not have 1m and 1n in our set, because 1 can only go to one item in the range. It can either go to m or it can go to n. It cannot go to both. So it's very important that you understand that not every correspondence that we're going to see is going to be a function. It may be a relation. The function here, again, is special. So that's what we're looking for. And there's all different types of notation that you can see about functions. In this class, we're basically just going to focus on function notation, which is this last one right here, where it says y equals f of x. So that is what we are going to use. F of x is just a fancy way of saying y. What it reads technically is the function in terms of x. So we are going to write a function that is going to, the only variable we're going to use is x. So inside the parentheses is the variable that we're going to use in our function. It's often used to replace the y when you're using equations. So just know that the y would be your f of x, and the x would be those domain values that you're going to be plugging in. All right, so let's start and talk about how do we know if a relation is a function. So let's look at the one on the left. Okay, the thing you're looking for is you want each domain value to go to only one value in the range. So you want to see an arrow from that domain value to only one value in the range. And notice here, every single value that we see in our domain only has one arrow going to it. You can have the arrows going to the same value in the range. So like 1 and 2 both have 6 as their range value. That is fine. 1 only goes to 6. 2 only goes to 6. That's what you're looking for. Notice over here, so this one is a function. So this is a function. Notice the one on the right, however, especially here, shows right up at the top with that 6. 6 is going to both 1 and to 2. It cannot go to both. It has to go to one or the other. So that domain value cannot have two different range values that correspond. So this one is not a function. This representation over here would just be a relation. It's a relation only. So functions are just special relations, that's all. Right, here's another example. Is this relation that I've just shown you, is this set of ordered pairs, is this a function? So again, you're going to look. 1 is only going to 2. That's good. 3 is only going to 4. 6 is only going to 5. And 8 is only going to 5. So that is beautiful. That is a function because each element in the domain is only going to one element in the range. Now, there are other ways that our functions can be represented. If we're given a graph, how do I tell if it's a function? There's a great test. It's called the vertical line test. All you have to do is draw a vertical line through the graph. If any vertical line intersects that graph in more than one point, then that is not a function. But if you can draw any vertical line and it will only cross the graph once, then that is a function. So here are some examples for us to do some quick rundowns. All right, so let's look at the one on the far left. Notice no matter where I draw a vertical line, and again, I could draw multiple ones. It only hits once, only hits once, right? No, I'm just hitting one time every single time. So this graph is a function. Whatever that is, I can write it in function notation. All right, look at the next one. This can be a bit confusing. This is called a piecewise function. And we will talk more about those later. Piecewise functions are pieces of functions that are kind of smushed together into a like Frankenstein function. Each piece is a function itself. The only thing you have to be careful about is look at right here, where this function ends and then this piece of function starts again. But notice if I draw a line, it's only going to hit the function once because right here, that point is not included. It is included here. So technically, my vertical line only hits it once because that top point is not included, the bottom one is. So this is also a function. Those can be a bit more challenging though, so I will give you that. They can be challenging. And the last one on the far right, notice that is not a function because if I draw, I will hit it here, I will hit it here. So this is not a function. So when you are dealing with graphs, I find it much easier to determine if it's a function or not, just because we have this quick, easy vertical line test. When you are given the graph of that function as well, you can also find the domain and range from those values. So again, reminder that the domain is always the first input, which is always our x. So when we have an ordered pair on a graph, it's always x, y. So the x's will be the domains, and again, I'll write that at the bottom, x, y, right? Those are going to be our ordered pairs. So the x's will be the domain, and the range will be the y's. Sometimes you will hear people call them inputs and outputs. So the x is the input, the y is the output. It all means the same thing. So when you're looking at a graph and you want to find the domain and range of that function, what you're looking for is all of the values that are in, so the domain, we're going to look for all the x values that work for this function. So if you look at this, you will see that my x's start at 2 and 2 is included, -2. That is the smallest x value that is on our function. And as we follow, notice there's no gaps, there's no jumps, there's no anything. And then we just keep continuing on this piece of the function and we stop at 1. Notice my endpoints are included. So my domain value, we're going to start at -2, that is included. And we continue along this function until we get to x equals 1. And at that point, when x equals 1, our function ceases. So that is our domain for that function from -2 to 1. Again, that is written in interval notation. They could ask you to write it in set builder notation. They could ask you to write it as an inequality. There's a million ways that they could ask you to write that answer. Interval notation is probably the most famous, so I'm just going to stick with that one. All right, then you're going to repeat this process with the range. Choose a different color. All right, so range, you're going for the y values. So at this point where I start on the left, because we read every graph from the left to the right, it starts at a y value of 0, right? That is the point -2 comma 0. So we're starting at 0, and 0 is included. And I'm going to go up and up and up and up on the graph, and up and up and up. And when I end, I am ending at a y value of 3. And notice that value is included as well. That endpoint is 1 comma 3. So I'm ending at 3, and that is also included. So there is how you find domain and range when you're dealing with a graph. It can be challenging. You have to make sure that you remember very carefully where you're beginning and where you're ending, and what you're looking at, the x's or the y's. So take a little bit of extra time with these. All right, so here's another example. Again, my graph, if I'm starting with the x values, I am starting at -2. So that is my farthest to the left on the graph is -2. And notice -2 is not included. Notice it's got an open circle right there. So round parenthesis -2, because -2 is not included. And as I follow my graph, reading it to the right, it ends when my x value is +1. And notice +1 is included. So +1 will have that square bracket. Then I can continue on to my range values. Remember, range values go with the y's. So we're going from the bottom to the top. So my y value, the lowest y value I see is a -1. -1 is included because it is, right? Notice it doesn't have an open circle there. So we're starting at -1 in our y values, and -1, oops, I almost put a round parenthesis. Let's fix that. All right, square bracket because it is included. And then as I go up on the graph, notice the highest y value I get to is 2, but not including 2 because that is an open circle. So 2, but I don't include it. So that one is, the 2 should have a round parenthesis. Again, every little tiny thing matters when you're discussing notation, so please make sure that you're paying extra special attention to those. All right, I have 2 more examples. So maybe you want to try these on your own. So here's the first one. Again, here's the graph. I would like you to find the domain and the range. All right, so let's see how you did. So this domain value, notice I've got some arrows on here, which meaning that this parabola is going to keep going and going and going. And the higher it gets, the wider it gets. So this is going to keep going forever and ever and ever. So that means my domain is going to be from -infinity to +infinity. Notice infinities always have the round because they are not actual numbers. So keep that in mind. They always get those round parentheses. But my range, notice this is the lowest value right here. So that is the range. So -1, -2, -3, -4, -5. So it starts at -5, and that point is on the graph. And then this parabola goes up and up and up forever. So we're going to go up all the way to +infinity. So you could have infinities in your domain and range values. So just keep that in mind. It's not just particular numbers. It may go out, it may go off to +infinity or -infinity in either direction. Or like in our case, the domain went to both directions. All right, you may also see graphs that look like this, where they're just points. So this is literally just a relation. It is a set of ordered pairs. They just graphed them instead of giving you the written ordered pairs. So when we look at our domain, we're going to have very specific values. So the farthest one on the left I see is 1. So I have a domain. I have my values are 1, comma. The next one I see, I do have a dot at 2 when the x values are 2. I have a dot when my x values are 3. I have a dot when my x values are 4. 5, and also 6. So there is my domain, 1, 2, 3, 4, 5, 6. Then we're going to do the range as well. So in the range, you're going from the y's. So you want to look at the y-axis, start the farthest down, right? Instead of starting at the left, we're going to start at the bottom. So the lowest one I see is -1, comma, and then there is one at 0, and then there is one at +1, and there is at +2, and one at 3. And then there's a gap. There's nothing at 4, there's nothing at 5, but there is at 6. So there is your domain and range for that function. All right, so we've talked about how do we tell if it's a function, when it's a set, when it's a graph. The last thing we can talk about is how do we tell if something is a function if it's an equation. So if you have an equation, you need to be able to solve for y. There's some caveats though. When you solve for y, you have to make sure that there's no plus or minus, because if you have a plus or minus in your answer, that means each y value is going to have two different domain values. So you need to be super careful with those, because those plus or minuses are usually a dead giveaway that it is not going to be a function, because you're going to have an x value that it's going to have a plus or a minus in front of it. So you may simplify it out and it comes out to 2. Well, if it's plus or minus 2, that means that that value of x, you're going to have a value of positive 2 as your range and a negative 2 as your range, and that you can't have. It can only have one. So pluses or minuses, you should definitely steer clear of. Anytime you see a y squared, it's not going to be a function, because if I wanted to solve for y, so I could use function notation and solve it for f of x, that would mean I'd have to solve for y, and if there's a y squared, that means you're going to have a plus or minus. So those are things you should look for. You should also look for certain things, like we are only going to do 2 variables. So if you see 3 variables, right now we don't have the skills to do that. So again, there's lots of things that you could look for, but here's the first one. So determine whether the equation is a function, defines y as a function of x. So if you want to, you could try and solve for y. So first I would subtract the x squared from both sides, and then I'd have to get rid of the squared, I'd have to take the square root. And everybody knows when you take the square root, you're going to get a plus or a minus, right? Because negative 2 squared is 4 and positive 2 squared is 4. So automatically I know I'm going to end up with a plus or minus and then a square root over here. And that would not work because of this right here. And again, that goes back to there's a y squared. So this is not a function. And later on, we will talk about how we can restrict things so that we know that they will be a function. So we could just say, hey, we're just going to neglect that negative sign and just do the positive part. Then it becomes a function, because you're neglecting that other half of the range values. So that's things you can do as well. But in this case, the way it's written, it is not a function. All right, what about this next example? Right, so again, you're going to solve for y. So the first thing I'm going to just do is I'm going to move the x squared to the other side. And then I'm going to get rid of this negative sign in front of the y by changing all my signs. And lo and behold, I could solve for y. So when that happens, you can just replace the y with the f of x, and there would be your function notation. So this is a function. And that's the nice thing about function notation, is when you see it, you automatically know it is a function, whatever they're talking about, and you don't even have to think about it. So it just kind of gives you some heads up about things. All right, so we have a couple more things to talk about functions, but we're going to save that for next time. So come back and we'll talk a little bit more about functions.